Alright, students, this is my first attempt at this little video podcast thing, so bear with me. This is over lesson 5.3, simplest radical form. Specifically, we're looking at, square roots, or, beyond that, nth roots. So, the number under the square root sign, or under the radical sign, that's what we call a radicand, the number under the radical sign there. In our example here, so I can highlight. There we go. That's A. That's our radicand. It's the number under the radical sign. The order, or the index, is the number indicating the root being taken. So, for instance, if I had, the cube root of x, the order in this case would be 3, or the cube root. So some definitions. We see we have the nth root of a. We can rewrite this like so, which the n and the nth root, the exponent and the nth root, just cancel out, so it's just a. So if you would have the square root of something squared, so let's say the square root of x squared, those squared and square roots would cancel out. I didn't need to put that little 2 in there. And it would just be x. Look below, we have the nth root of a times the nth root of b. We can rewrite this as the nth root of a times b. We also have, the mth root of the nth root of a. We can rewrite this where basically we're just multiplying the orders together, so m times n of a. And then the last one, you see we're dividing, so the nth root of a divided by the nth root of b. We're allowed to rewrite this and say it's the nth root of a over b. B cannot be what number? 0. Because that would give you undefined, and we don't want that. And for most of this stuff, whenever we have a variable or a or x or whatever, we're going to just assume that they're non-imaginary numbers here. So if a in this case would be a positive number. Let's do some examples. So if we look here, we have the 5th root of 4 to the 5th power. Well, we know that the 5 and the 5th root cancel out, so it's just 4. And let's see, on example B, there's supposed to be a cube right there. We have the cube root of 2 times the cube root of 3. Well, we can rewrite this as the cube root of 2 times 3, or just the cube root of 6, and we're done there. Let's see, letter C, which this is on page 158 of your textbook if you're following along in your book. For letter C, we have the 3rd root of 5 squared. So we can rewrite this as 3. Ooh. How to fix that? There we go. 3 times 2, in the order right there, of 5. So the 6th root of 5. And lastly, we have the square root of 7 over square root of 3. We're allowed to rewrite that as 7, the square root of 7 over 3. Example 2. So here we're just looking at the root of sum and products. So look at the first one, the square root of 16 plus 9. This is not equal to the square root of 16 plus the square root of 9. Because if you look at it, if we did the first part, the square root of 16 plus 9, well, 16 plus 9 is 25, so the square root of 25 is 5. But look at the right side here, square root of 16 is 4, square root of 9 is 3, 4 plus 3 is 7, not 5. Now we look below, when we're multiplying, we're allowed to split them up. And we're allowed to say that the square root of 16 times 9 is equal to the square root of 16 times the square root of 9. So in this case, 4 times 3, or 12. We're allowed to do that. That's cool. Alright, example 3. We're removing perfect square factors here. So here we have the square root of 75 and the square root of 72. We're just trying to basically simplify those because we know that there are perfect squares that go into both of those. I would recommend knowing like the first 15 perfect squares. Like 1 squared up to 15 squared. I would recommend knowing those and probably like your first like few perfect cubes. I promise it'll be helpful in the long run. So if we look at 75, we know 25 goes into that. So we can rewrite this as the square root of 25 times the square root of 3. We know the square root of 25 is 5, so we reduce that. So, make that neater. 25, square root of 75 is equivalent to this. Keeps doing that. This is equivalent to 5 square roots of 3. Now look at 72. Let's see. I think the biggest perfect square that goes into that would be 6. No, 36. Sorry, that's what I meant to say. Teacher technique. So we have the square root of 36 times the square root of 2, because 36 times 2 gives you 72. Square root of 36. We know that that's going to be 6 square roots of 2. This is fun stuff. Alright, example 4. Now we're removing perfect nth power factors. So we're just reducing now when we have specifically exponents and such. So the first example, square root of a cubed times b squared. So let's rewrite this because we're dealing with squares. So we want to rewrite that a cubed so we can pull out, pairs of a, or a squares, basically. So we can rewrite this as a squared times a, the times sign, times b squared, which is the same thing as the square root of a squared times the square root of a times the square root of b squared, which is just ab square root of a. That's as low as we can go. If we look at the next one, the cube root of 40. So let's think of a perfect square, or no, perfect cube that goes into 40. We know 8's a perfect cube. 8 goes into 45 times, so we're allowed to rewrite this as the square root, or the cube root, sorry, of 8 times 5, or the cube root of 8 times the cube root of 5. We know the cube root of 8 is 2, so we can write this as 2. I don't like that. 2 cube roots of 5. Alright, another part of example 4. We have the fifth root of 74x to the 8 y to the 12th. So we're allowed to rewrite this as, let's look at that, 64. So I'm trying to find a perfect fifth root, or a number that can be a perfect fifth. So we know that 64 can be broken down, and this could be, kind of guess and check until you get to know some of these. But we're allowed to break this up into 32 times 2. Because, let's see, 32 is 2 to the 5th power, right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So we can break that up. That x to the 8th, we can rewrite that as x to the 5th. That way we can kind of move an x out of that. Times x cubed. And then looking at the y, we want to break that y to the 12th into one number that's a factor of 5, because we have the fifth root, and then whatever left over. So, we add the exponents when we're multiplying, so we can, the smallest, or no, the biggest multiple of 5 that goes into 12 will be 10. So we can break that up into y to the 10th times y squared. So let's kind of break some things down. We know that the fifth root of 32 is 2. So that's outside the radical. So this right here, we moved out. If you look at x to the fifth power, the fifth root of x to the fifth is just x. Now, the y to the 10th, the fifth root of that would be y squared. Because you've got basically right there, it's going to be the fifth root of y to the 5 and the fifth root of y to the 5, which pulls out a y and another y, so y squared right there. So then what's left over, we write in here, we got this 2, we got x cubed, and we got y squared. That would be our final answer. That's a fun one. Alright, example 5, reducing the order of the radical. Remember, the order is the that little number, like 6 and 8 in these two examples. So here we have the sixth root of 8. We can rewrite this, which you can definitely do some of the stuff in your calculator to give a more exact answer, but, well, decimal in some cases. Sometimes you get a nice pretty integer. We're allowed to rewrite this as the eighth root of, oh wait, skipping ahead, the sixth root of 2 cubed, because we know 2 cubed is 8, right? Now, this is the same as 2 to the 3 over 6, which is the same as 2 to the 1/2, which is the same as the square root of 2. Look how pretty that looks. Let's look at the next one. We have the eighth root of 16. So let's rewrite this as the eighth root of 2 to the 4th power, because 2 to the 4th will give you 16, which equals 2 to the 4 over 8, or 2 to the 1/2, which is the square root of 2. Let's do another one of these. Let's see, we got the fourth root of 9 over the cube root of 3. Well, 9 we know is 3 squared. So on the top we have the fourth root of, let's see, 3, oops, not that. On the top we have 3 to the 2/4 over 3 to the 1/2. Right, because remember square root is 1/2, which is just here, 3 to the 1/2 over 3 to the 1/2, which is 1. That one's kind of cool. Let's do one with variables. Here we have the ninth root of 27, x to the 6, y to the 12th. So let's rearrange this a little, or kind of redo this a little bit. Let's make that 27. We know that's 3 cubed. X to the 6. Let's look at that y. So it's y to the 12th. 9 goes into 12, so let's rewrite this as y to the 9th. And let's see, left over would we have 3 more, so y cubed. Extend my radical. So now we have 3 to the 3 over 9, x to the 6 over 9, y to the 9 over 9, and y to the 3 over 9. So this is just 3 to the 1/3, x to the 2/3, y to the 1, and y to the 1/3. So let's put some stuff under the radicals. This y doesn't have a radical, so it's going to go out front. I notice cube root, cube root, cube root here. So this becomes the cube root of 3. Now this x has a 2 in it, so it's going to be x squared with the 3 on the outside. And then y to the 1/3 cube root of y. That will be our final answer. Alright, example 6, we are rationalizing the denominator. Basically, in these examples, we don't like square roots in the denominator. I don't know, mathematicians just don't like them. So we're going to get rid of them here. So we look at the square root of 2 fits. Let's rewrite this as the square root of 2 over the square root of 5. Now, we're trying to basically make that square root of 5 positive. So what we're going to do, we're going to multiply, or not positive, we're making it not a square root. We're trying to get rid of that square root there. It's late. It's alright, kiddos. So we're going to multiply by the square root of 5 over 5. Because watch what happens when we do this. On the top, we're going to have the square root of 10. You're allowed to multiply, you get 2 and your 5. On the bottom, if we multiply those two 5s, we have the square root of 25. We know that the square root of 25 is 5, though, so we have the square root of 10 over 5. Mathematicians like that better rather than having the square root of 2 and square root of 5. This will be our final answer. It's rationalizing the denominator. Step 1. We'll do more of it later, but this is kind of the basic stuff. Let's see another example. Here we have square root of 18 on the bottom. So let's multiply to get rid of. So let's see. Now the book rearranged the 18. You can multiply by square root of 18 over square root of 18. You're going to get the same answer. We can go ahead and do that. Your textbook does it a little bit different. They simplify your square root of 18 to 3, let's see, let's place 3 radical 2. So you can do it that way, or you can do it this way. Because on top, we know we're going to have 5 square roots of 18. On the bottom, the square roots cancel out, and we just have 18. But we're not done here. We're going to look at that square root of 18. Think of a perfect square. What's the biggest perfect square that goes into that? So we can rewrite that as 5 times the square root of 9, right? Because 9 goes into it 2 times, and 9 is a perfect square. So bring it down here. Square root of 9 is 3. So we now have 5 times 3 outside, times the square root of 2 over 18. 5 times 3 is 15. So 15 radical 2 over 18. We want to reduce that 15 and that 18 to give us, let's see, reduce by 3 to give us 5 square roots of 2 over 6. That would be the final answer. Alright, example 7. This is another rationalizing the denominator. But now we're dealing with cube root. So let's rewrite this as the cube root of 2 over cube root of 3. Now, this one's a little bit weird. Rather than multiplying by the cube root, because that's not going to do anything. Here we need to multiply by a number under the radical so that we get, so that our, basically the number under the radical, the radicand, needs to be a perfect cube in this case. So for instance, in this case, if we multiply the top and the bottom by the cube root of 9, let's see, on the top we have the cube root of 18, which we don't care about too much. But on the bottom, 3 times 9 gives us 27. We have the cube root of 27, which we know is 3. So we have the cube root of 18 on top over 3. Alright, last example. This is a fun one. which means you guys will hate it, but it's a fun one, I promise. We're simplifying this a lot. We've got the square root of 1 over 2a squared plus 2b to the negative 2. First step, let's rearrange this a little bit. So we've got the square root of 1 over 2a squared plus, now, the 2b to the negative 2, the 2 stays on the top, but the b to the negative 2, we want to move that b to the bottom. That negative 2 becomes positive 2. Now we get to find Eli's favorite part, the LCD, because we're going to add two fractions here under the radical. We're adding the 2a squared and the b squared. The LCD would need to be 2a squared b squared. So let's see, we're going to multiply the first fraction by b squared. So we're going to have b squared over 2a squared b squared plus multiply the second fraction by 2a squared, so 4a squared over 2a squared b squared. I'm going to rewrite this a little bit to make it neater. Square root of b squared plus 4a squared over 2a squared b squared. Now, we don't like square roots on the bottom, but let's kind of take this step by step a little bit more. Uh-oh. Erase that little mark I just made. So we've got the square root at the top, which we won't do much with, over the square root at the bottom. Now, 2a squared b squared is what we have. But we can pull out an a and pull out a b, because we would basically square root everything in there. 2 we can't square root anymore, so we would have the square root of 2. But square root of a squared is just a, square root of b squared is b. So, the numerator would stay the same, b squared plus 4a squared. Denominator would now become, I'm going to pull the ab out front, square root of 2. We don't like square roots on the bottom, so multiply by square root of 2 over square root of 2. I'm going to have to add a new slide here. So let's see, this is where I was. Square root of b squared plus 4a squared over ab square root of 2 times the square root of 2 over square root of 2. So the denominator is just going to be 2ab. But the numerator is going to be the square root of 2 parentheses b squared plus 4a squared. Because that 2 it's not going to be marked out front, but we would just distribute it. And the book didn't go ahead and distribute this. You can, but you can also just leave it just like this. Now we can't cancel these 2's out because this is the square root of 2, remember, on the top, but the bottom is just 2. And that is my last example. Sorry this one was a little bit too long. Work on homework problems, which I'm going to have you do for homework, which we can work on in class now. Page 161, numbers, I think I said 5 through 63 odds. Make sure you behave for my sub and just be the awesome students that I know you guys are. And I will see you on Friday.